Okay, in this video, we're going to be doing Calc BC Problem Set number 12. The problems in a playlist are in the description below. Let's take a look. Number 1, evaluate each of the following limits. Notice how they're all kind of different. So we're going to look at 4 different things, and they're all limits, but they're all a little different. So the first one, limit as h approaches 0. As soon as you see this, you got to think limit definition of the derivative. So if that's what you're thinking, you have to identify the function and then find its derivative, right? So it's f of x plus h minus f of x over h. So in this case, I think that f of x is the function secant squared of x, right? That's the thing we're plugging x plus h into. It's also f of x plus h minus f of x, right? So f of x is the thing being subtracted, so secant squared. The derivative of this, chain rule problem, so you're going to get 2 times the secant of x times the derivative of secant, which is secant tan. Definitely memorize all your derivatives of your trig functions, and this simplifies to 2 secant squared times tangent. So that's it for the first part. Not really that bad. None of them are really bad, but they're all a little different. So here we have the limit as x approaches positive infinity of the square root of 3x squared plus 1 over 1 minus 3x. So your initial thought on this might be to try to use L'Hopital's rule. This is a type of problem where L'Hopital's will loop on itself, like eventually you get back to the original thing that you were dealing with, or something very similar to the original thing, so you don't really want to employ L'Hopital's on this. Instead, what we'll do is I'm going to factor the highest power of x that I possibly can out of the radical. So I'm going to say it's the limit as x approaches infinity. So inside the radical, I can take x squared out. So it's x squared, the quantity 3 plus 1 over x squared. So remember, when you're factoring out, it's the same as dividing, essentially. So 3x squared divided by x squared, and then 1 divided by x squared, and then our x squared sits on the outside. The square root of x squared is the absolute value of x. So we get x goes to infinity, absolute value of x, square root of 3 plus 1 over x squared over 1 minus 3x. Now, if you're going to infinity, the absolute value of x is just equal to x, so we can replace absolute value of x with x. So we're going to have limit as x approaches infinity of x, square root of 3 plus 1 over x squared, over 1 minus 3x. Now divide everything you see by the highest power of x in the denominator, which is x to the first. So when I divide the numerator by x to the first, the x's just cancel. And then our denominator is a little more interesting. You have 1 divided by x, and then minus 3x over x is just minus 3. Now, if you go to infinity, the 1 over x squared and the 1 over x go to 0. So we're just left with radical 3 in the numerator, negative 3 in the denominator. Our final answer is negative root 3 over 3. Okay, let's take a look at the next thing that will involve a limit. So here we have the limit as n approaches infinity, the sum from 1 to n of a bunch of stuff. Well, as soon as you see the limit as n approaches infinity of the sum from 1 to n, you should be thinking this is probably a definite integral, right? So sometimes you look at a limit and you're like, that's definitely a derivative, and other times you're like, that's definitely a definite integral. This is a definite integral. So we got to work out of what. So I like to go through and try to find delta x. This problem is weird though, because like, what is this? It's got pi squared. It's over n, so I'm thinking it's probably related to delta x. So I'm going to look through and try to find a different place where delta x is. And you can see it's here. We have 2 pi k over 3n. So I think delta x is 2 pi over 3n. So since I'm thinking that it's 2 pi over 3n, I'm going to rewrite this thing to just kind of look more normal, I guess, right? Like I want it to look like base times height. So the base should be 2 pi over 3n, and then the height should be whatever the function is. So I've rewritten it. Let me go back. I rewrote it. I keep the limit, so I still have the sign part, and then I'm taking this 4 pi squared over 9n, and I'm breaking it into, I think that delta x is 2 pi over 3n. So I want 2 pi over 3n, and then whatever else is left. So my 2 pi over 3n, and then I still have a 2 pi over 3 left over. So that's where 4 pi squared over 9n is coming from. It's very weird. All right, so I think that delta x is 2 pi over 3n. I think that x sub k is the thing that I'm plugging in. So I think that x sub k is, the thing being plugged into sign is overtly pi over 3 plus 2 pi over 3n times k. That's x sub k. Now we use x sub k to find the bounds of the integral. So you let k equals 0 and k equals n. That'll tell you where you start and where you stop. So if k is equal to 0, we just get pi over 3. If k is equal to n, we get pi over 3 plus 2 pi over 3, which is 3 pi over 3, which is pi. So those are going to be the bounds. Now, what is our function? Our function is pretty straightforward, except for whatever reason, there's just this extra 2 pi over 3 hanging around. I don't actually know why I put that, but I think my function is sine of x times 2 pi over 3, or 2 pi over 3 sine of x. I don't know. So our definite integral will be the integral from pi over 3 to pi, 2 pi over 3 sine of x dx. This is actually a pretty straightforward thing, right? The antiderivative of sine is negative cosine, so we'll get negative 2 pi over 3 cosine, and then we're going to go from pi over 3 to pi. So you have to remember your unit circle values. Those are important. So negative pi over 3. The cosine of pi is negative 1. And then the cosine of pi over 3 is 1/2. So we have minus 1/2, right? Because fundamental theorem just has a minus there. And then 1/2. So that's negative 2 pi over 3 times negative 3 over 2. So those cancel, and we just end up with a final answer here of pi overall. So I guess that's why that 2 pi over 3 is there, so that the answer ends up like looking kind of nice. I don't really know. Let's take a look at the next one. We're going from 1 to infinity, x cubed e to the negative x squared. If you've been doing all the problem sets, you know that we did something really similar, maybe in fact this problem. So I'm going to do integration by parts, but there's kind of an issue, right? So like you initially maybe think like, oh, I'm going to let u equal x cubed. Then the problem is you can't integrate e to the negative x squared. So instead, we take x cubed and we break it into x squared times x, and we save the x to be part of e to the negative x squared. So really I'm going to say that u is x squared and dv is x e to the negative x squared. The reason I'm doing that is because it works. And part of getting really good at calculus is just doing a lot of problems. Eventually you've seen things before, so you're not intimidated and you just kind of like know how to deal with them. This is an example of that, where you kind of save a power of x and use it for part of your du in another part of the problem. So here, if u is x squared, then du is going to be 2x dx. And then v is going to, so there should be a negative 2 by the chain rule, so there's going to be negative 1/2 e to the negative x squared. So we get uv minus the integral of v du, which is going to give us negative 1/2 x squared e to the negative x squared. And then, so I'm doing an indefinite integral to begin with. I maybe forgot to mention that. I don't want to have to keep writing like the bounds and dealing with the improper integral and all that. So I'm just doing an indefinite integral. I'm going to get an answer to that. Then I'll use the fundamental theorem. That's my plan. So we have uv minus the integral of v du. So minus 2 times negative 1/2 becomes plus 1. So we just have plus the integral of x e to the negative x squared. And that we can integrate. That's basically what we had for dv before. So we still have this, and then we'll get a minus 1/2 e to the negative x squared. And then there's a plus c, but we're doing the fundamental theorem, so I'm not going to worry about that. So our original integral here, we know by the fundamental theorem, actually, we need to deal with the improper integral, right? We have to change this and say it's the limit as b approaches infinity, because when you're using the fundamental theorem, you can't have infinity, you have to have finite bounds. So what we do is just pretend. I mean, it's like make-believe. We say like, oh, it's going to be b, and we'll do the fundamental theorem, and then it's like, what if b coincidentally went to infinity? That's essentially what we're doing, but that's fine, because that's what we all agree to do. So this will be the limit as b approaches infinity. We're going to sub in b, right? Also, what I'm going to do is e to the negative x squared, when I sub in b, is e to the negative b squared. I'm going to put it in the denominator with a positive exponent, so it's a little more obvious what's happening here. So going up, we know the antiderivative, right? That's what we found. It was negative 1/2 x squared e to the negative x squared minus 1/2 e to the negative x squared. So we already knew that. So I subbed in b for the first part. I'm going to sub in b for that second part there with this. Then minus, when you plug in 1, it's just like gross. You get negative 1/2, 1 squared e to the negative first minus 1/2 e to the negative first. What's nice about this, if you want to call something nice about this, is that everything that has e to the b squared in the denominator, I don't know if you can hear the giant helicopter that I think is going over right now, so that's kind of crazy. Everything that has e to the b squared in the denominator is going to go to 0 when b goes to infinity, right? Because exponentials grow faster than essentially anything else you run into. So those are going to go to 0. So all that's left is that right-hand part, the minus quantity -1/2 e to the negative first minus 1/2 e to. If you combine everything there, you just get e to the negative first. That is the value. So that's 4 different ways that limits will come up. And there's even more than that. But just like, do a couple practice problems, you'll be okay. Let's look at the next one. Use the table of values of the derivatives of f of x at x equals 2 to answer the questions that follow. All right. Third degree Taylor polynomial. Hopefully we're pretty good at this point. You got to memorize that formula. So our polynomial is going to be the value of the function, which is -5. And then it's going to be first derivative x minus 2 to the first over 1 factorial, which is 2x minus 2 to the first over 1 factorial. Then it's going to be second derivative x minus 2 squared over 2 factorial. So plus 4 x minus 2 squared over 2 factorial. Then it's going to be third derivative x minus 2 cubed over 3 factorial. So it's going to be 5x minus 2 cubed over 3 factorial. There you go. Got to get amazing at writing those. Those should cause you no stress. For part B, approximate f of 2.1 using the third degree polynomial above. So all you're going to do is replace every x with 2.1. A thing that happens with these, which usually is an indicator that you've done it wrong, is if when you sub into your polynomial, you still have like huge things, well, big things, being raised to powers, then you're probably wrong. Watch what happens. Because we have 2.1 minus 2, we just end up with these little 0.1s being raised to powers. If you still had 2.1 there, that's a really good indicator that you have forgotten the center of your polynomial, and you don't want to do that. All right, I'm not going to simplify this because I don't think it's going to help much. I mean, it's like going to be really close to, I don't know, -4.8, right? Because it's like -5, and then you got 0.2, and then everything after that is getting very, very small. So it's going to be close to -4.8, but we don't have to simplify that. We'll leave it. Let's take a look at the next part. Given that the fourth derivative of x is less than 0 and increasing for all x between 2 and 2.1, determine the maximum possible error for the value found in part B. Okay, so this is the Lagrange error bound. Some people freak out about it. There's nothing to freak out about. Just make sure you memorize the form of the error. If you have that memorized and you can figure out what m is, you're good to go. So here, we're being told that the fourth derivative is negative and increasing. So I'm gonna like sketch it. It starts at -4 and then it just like increases but stays negative. So then if I drew the absolute value of that, it would start at +4 and then decrease but stay positive because it's absolute value. So I think what we can do is we can say since the fourth derivative is less than 0 and increasing, the absolute value of the fourth derivative will be positive and decreasing. What's important about that is that means that the absolute maximum, or the maximum of this thing on the interval from 2 to 2.1 is definitely 4. It's definitely at the left endpoint. I just confused left and right. It's at the left endpoint because it's positive and decreasing. Well, because it's decreasing. It's at the left endpoint. Okay, so I'm going to use this notation, the maximum on the interval from 2 to 2.1 of the absolute value of the fourth derivative. So this is how you can write down basically m in the formula. The maximum on 2 to 2.1 of the absolute value of the fourth derivative is equal to 4. And since that's the case, we can say that the absolute value of the error is going to be that mysterious value of m, which is the 4 that we just found. It's less than 4. And then we have the absolute value of 2.1 minus 2 to the, if it's fourth derivative that you're using to find m, it's to the fourth. If you use the 12th derivative, it would be to the 12th. And then over 4 factorial. So the power and the factorial will always be the same. It's super inconvenient that I also happen to choose that m was the same value. That will not always happen. If we were to simplify this, I don't know, 4 over 4 factorial, the 4's cancel and you just get 1 over 3 factorial, so that's 1/6. And then you have 0.1 to the fourth, which I'm going to say is 1/10 to the fourth. So 1 over 6 times 10 to the fourth. Okay, that's the entire problem set. I hope this was helpful, and good luck.